All right. So for about the past 3 years now of my graduate school career, I have been in pursuit of the mystery reservoir. I think the field has been in pursuit of it for some decades now, so I'm a little bit late to this party, but I have some new records from the Eastern Equatorial Pacific that we think provide some new insight to this long-standing problem. All right, so the time period of interest here is the last glacial termination. This is a time period of global warming. So I'm showing warming global temperatures here between 22 and 8,000 years ago. At the same time, we see rising atmospheric carbon dioxide levels, shown here in these yellow circles, rising in sync with Antarctic temperatures, shown in red. So over this time period, we see about an 80 parts per million rise in atmospheric carbon dioxide levels. So the question, there's many questions to talk about in terms of the last glacial termination, but the one I'll focus on here today is where was all this carbon being stored during the last glacial termination, or during the last glacial period? And then secondly, what path did it take back to the atmosphere? So one of the leading hypotheses at this point for where this mystery reservoir was that it was in the deep Southern Ocean. So this is a schematic from Skinner et al. In 2010. It shows that during the last glacial period, the Southern Ocean water column was more greatly stratified, potentially due to extension in the sea ice extent, as well as northward shifted westerly winds. And as a result, you have greater stratification and reduced ventilation of the deep Southern Ocean. This allows old carbon to build up here, and it's sitting there for a long period of time, so its radiocarbon clock is ticking down. So you have less C14 relative to carbon-12. So you get a very low cap delta 14C signature, and because this is composed predominantly of mineralized organic matter, you also have a very light delta 13C signature. As we move into the termination, we see rising temperatures, sea ice extent is reduced, southern westerly winds start to shift southward. And as a combination of these effects, you see a reduction in the strength of stratification in the Southern Ocean and mixing upward of this deep ocean carbon. Some of the carbon will mix up to the surface and then exchange immediately with the atmosphere in the Southern Ocean. But the idea is that the majority of it gets resubducted in Antarctic intermediate water and mode water. So to test this hypothesis, we look for signatures of low cap delta 14C and low delta 13C in Antarctic intermediate water and mode water during these two pulses, during Heinrich Stadial 1 and the Younger Dryas, all over the world. Okay. So some of the best evidence that we see for that the Southern Ocean was at play here comes from a record from off the coast of Baja, California, from Tom Marquito's group at the University of Colorado. I'm plotting here on the global map the global extent of Antarctic intermediate water and where it's important. So this record comes from kind of the northernmost location in Antarctic intermediate water. So they're looking here at the shells of benthic foraminifera, looking at the radiocarbon content of these shells. And these benthic forams are coming from intermediate water depths where Antarctic intermediate water is important. So here I'm showing that record in red. This is benthic foraminiferal cap delta 14C plotted on this right-hand axis. We're looking at 22 to 8,000 years ago. Also shown here is, again, the atmospheric carbon dioxide levels in yellow, these yellow circles, rising in two pulses during Heinrich Stadial 1 and the Younger Dryas. Also for reference is atmospheric cap delta 14C in purple. So we see these strong decreases in atmospheric cap delta 14C, suggesting that old carbon, radiocarbon deplete carbon, is getting pumped back into the atmosphere during this time period, in sync with rising atmospheric CO2 and radiocarbon deplete values at Antarctic intermediate water depths near Baja, California. So there are these two really strong depletions. All right, so if we see these really strong depletions at the northernmost extent of Antarctic intermediate water, we should be seeing this pretty much everywhere else. So a number of other groups have tried to reproduce this record at kind of all of these diamond shapes, and I won't be able to talk about all of them today. So I'm just going to be focusing on the ones that are colored in, on the one I just showed you, a record from the Southeast Pacific from Brian, 2010, his thesis, and then a record from the Southwest Pacific. And then I'll be adding two records, another record from just off the Galapagos platform and just south of the equator, and 2 records from the northern Peru margin. I'm plotting the locations of these cores in terms of depth and latitude on a cross-section of the upper water column in salinity. So we see that Antarctic intermediate water is characterized by this very low salinity tongue coming in here at intermediate water depths. We have 2 CDH23 and CDH26 are our 2 cores from the northern Peru margin, and the core plotted here, GGC43 and CDH41, which is the splice of 2 cores, is at 600 meters. So all 3 of these core sites are being bathed by subantarctic mode water and Antarctic intermediate water. Age models for these cores are based on planktonic C14 dates, assuming a constant reservoir age. We interpolate between age control points using a polynomial fit. On the left-hand side is our Peru margin cores, and the 2 cores from the Galapagos are plotted here on the right. All right, so these are our 3 records. Plotting for comparison is the atmospheric radiocarbon record in purple. Our record from 1,000 meters in the northern Peru margin is in green. The record from 600 meters near the Galapagos is in gray, and then from 370 meters in blue is plotted here. So what you immediately see is that there's a really strong depletion in cap delta 14C values during the last deglacial at 600 meters. We see maybe a small decrease at 1,000 meters, but nothing really at 370. So we suggest that this really depleted signature is constrained between 370 and 1,000 meters, at least in the Eastern Equatorial Pacific. Now I'm going to compare that record from 600 meters to what I showed you earlier from off the coast of Baja, California. And then again, atmospheric radiocarbon. So immediately there are some similarities, and that, again, is that we see very depleted values during the deglacial period in both records. But there are some really important differences between these records. The first is that the Baja record really has these 2 very distinct pulses of old carbon during Heinrich Stadial 1 in the Younger Dryas. And ours, there really only is 1 during the Younger Dryas. I think this one data point might draw your eye to thinking there are 2. But if you look at just kind of the baseline glacial values, the only excursion for that occurs during the Younger Dryas. Part of the reason for that, of course, is that our glacial values are just a lot older. I won't be able to get into this too much today, but if you'd like to talk about that later, I do have some thoughts as to why that might be. To complement the cap delta 14C values, we also looked at stable carbon isotopes from benthic forems at the Galapagos site, and we see that during a period of radiocarbon depletion, we also see minima in delta 13C and a small minima during Heinrich Stadial 1 as well. So this further supports the idea that maybe this carbon is coming from the Southern Ocean. All right, so I've compared our record from the Galapagos to that near Baja, and now I'm going to look at 2 sites from the Southern Ocean. So these are 2 of the sites that are closest to the hypothesized source of this old carbon. All right, and so here I'm plotting these records. My record is here in gray from the Galapagos. Record from the Southeast Pacific is turquoise, and the record from the Southwest Pacific is plotted here in orange. What we first note is that there's no strong evidence for a large cap delta 14C depletion during Heinrich Stadial 1. Maybe a small decrease here, but then the values stabilize. During the Younger Dryas, however, we see a decrease in the Southeast Pacific in cap delta 14C at the start of the Younger Dryas, just like we see in the Eastern Equatorial Pacific. All right, so what does this all mean? We don't find very strong evidence for a signature of old carbon in Antarctic intermediate water during Heinrich Stadial 1, and there are a couple potential explanations for this. The first is that the Southern Ocean just isn't the source of the old carbon during this time period. But alternatively, it could just be a change in sea surface conditions in the Southern Ocean during this time period. So as we're mixing upward, mixing all this old carbon up to the surface, if it exchanged rapidly at the sea surface, you wouldn't be seeing this signature of old carbon at intermediate and mode water depths. During the Younger Dryas, we do find evidence for some old carbon in Antarctic intermediate water, and this suggests that air-sea exchange was relatively slow, and much of the carbon was resubducted in intermediate and mode waters. So in summary, our cap delta 14C records, they support a pulse of old carbon to Antarctic intermediate water during the Younger Dryas, and we think this The signal is vertically constrained to depths between 370 and 1,000 meters, at least in the Eastern Equatorial Pacific. These records don't support a flux of old carbon to Antarctic intermediate water during Heinrich Stadial 1, and I'd suggest that this is probably related to changes in the air-sea exchange rate relative to when these waters are being resubducted as intermediate and mode waters. Thank you.
Thank you, Samantha. We have plenty of time for questions. David?
Hi. How sensitive are your conclusions to the way you fit your age models using the polynomial?
So I have done some tests on if you took out some of the age control points, how much would it move? And you get basically the same signature. It moves. It's not that sensitive to age model errors, essentially.
So in your population of intermediate depth records, 500 meters, 700 meters, radiocarbon ages, delta C14 differences, equivalent to thousands of years of age difference.
Mm-hmm.
200 meters, 300 meters, seems completely non-visible. These waters are exchanging on time scale years, decades. Surface is exchanging with the intermediate depth on decadal time scales. When you think about the local scale process, the core water process, the main driving these radiocarbons.
Okay, I think you need to be aware of the potential for that to be happening, and I guess because we see this signature at so many different sites throughout the global oceans where Antarctic intermediate water is important, I think it's hard to argue that the same process is happening locally at so many different places. But I think it's definitely something that we need to be aware of when interpreting individual records.